In this video, we are going to learn how to solve a linear quadratic system of equations. Now, a linear quadratic system of equations is one that has a linear function and a quadratic function. And first, we're going to learn how to solve them by graphing. Then I'll show you how to do it algebraically by substitution. So to do it by graphing, I like to start with graphing the linear function first, which I'll do with a green pen. And I see here it has a y-intercept of 6. And a slope of 1, so that's up 1 over 1. And I've definitely graphed about enough points there. So now I'll draw a straight line through them. Just lining that up. And then I'm going to graph the quadratic function and look where the two functions intersect. And I'll do the quadratic one in red. Now, right now it's in standard form. If it was in vertex form, this would be easier to find out where the vertex is, and I can use the y-intercept to help me graph, which is 6. So I'm going to put this into vertex form by completing the square. So first I'll factor a negative out of those first two terms, give me x squared minus 5x. Then I'll add a particular number on the inside. And then on the outside, I will subtract that number times negative 1, whatever it is. And the number I add on the inside is half the b value here, squared. So negative 5 over 2 squared is 25 fourths. So I'll subtract 25 fourths times negative 1, which will then give me negative of x minus half of b squared. So x minus 5 halves squared. And on the outside, I have 6 plus 25 fourths. So that's 24 fourths plus 25 fourths, which is 49 fourths. So when I go to graph, I have to think about 49 fourths is 12.25 roughly, and then 5 halves is like 2 fifths. So the vertex for my graph is going to be at 2.5, which is in between 2 and 3, and about 12.25, about right here, which is not on a vertex point, so I'm going to get a few more values. I know the y-intercept is 6, so I can reflect that point. So 2.5 in, 2.5 out. It's over at 5, 6 is another point. And then I'm going to plug in 1 as well into this quadratic just so I can see where else it crosses, just so I have a few points to draw through. So if I plug in 1, that's going to be 1 squared, which is 1. So negative 1 plus 5, which is 4, plus 6, which is 10. And again, using the axis of symmetry through 2.5, I can reflect that over to 410. And there is my quadratic. And I can already see the two spots where they intersect. It happens at 0, 6 and at 410. Now, whenever you do this, solve these systems by graphing, you might want to double check that they are correct. We did find 2 of them, but also sometimes drawing graphs by hand can be a little inaccurate, so we're going to double check. So we're first going to plug in 0 for x and see that we get y for 6 in both of them. So y is equal to negative 0 squared plus 5 times 0 plus 6. Y is equal to 6. And the other one, we get y is equal to 0 plus 6. Y is equal to 6. So that one works for sure. Now let's try it with 4. So y is equal to negative of 4 squared plus 5 times 4 plus 6. That gives me negative 16 plus 26, which gives me 10. And then I get y is equal to 4 plus 6, which also gives me 10. So this also works. So those are my two solutions. Now let's look at another example with graphing. So here I have y is equal to x squared plus 6x plus 9, which is a perfect square trinomial. So Right away, I could write that as y is equal to x plus 3 squared, since that's how you factor x squared plus 6x plus 9. And if I go to graph this, my vertex will be at negative 3, 0. And I'll have a y-intercept over at 9. And I can reflect that across the axis of symmetry. So over at negative 6, 9 is another point. Now before I draw the graph, again, I like to get my linear function first. So I'll graph y is equal to x plus 3. So it's a y-intercept of 3. And a slope of 1, so up 1 over 1, or down 1 back 1. We'll see that they're going to intersect at negative 3, 0. The reason I like to graph the line first is now I'm seeing when I draw my parabola upwards, it looks like it's going to cross again around negative 2. And just to be safe that it does, if I were to plug negative 2 into this function, y is equal to negative 2 plus 3 squared, I get 1 squared, which is 1. So negative 2, 1 would be another point on the quadratic. So I can be doubly sure that they intersect there as well. So now when I go to graph, I can see my two intersection points. They happen at negative 3, 0 and negative 2, 1. And now to double check that they are correct, I'll plug in negative 3 into both functions. So negative y is equal to negative 3 squared plus 6 times negative 3 plus 9. So it's 9 minus 18 plus 9, which gives me 0. And into the other one, y is equal to negative 3 plus 3, y is equal to 0. So that one works. And then y is equal to negative 2 squared plus 6 times negative 2 plus 9, giving me 4 minus 12 plus 9, giving me 1. And then y is equal to negative 2 plus 3 for the other equation, which is also 1. They both work as solutions. Now, this can be a little tedious to have to graph every time you want to solve one of these. So here's an algebraic technique you can use to make the process go by a little bit faster. So here we have y is equal to negative x squared minus x plus 6, and y is equal to x plus 3. So we know what y is equal to. So what I can do is take the y is equal to x plus 3 and plug the x plus 3 in for the y in the original quadratic equation as a substitution technique, giving me x plus 3 is equal to negative x squared minus x plus 6. I can move everything to one side, so I'll add x squared. I'll add x, so plus 2x, and I'll subtract 6, so minus 3. And then I can just factor that equation, and I'll be able to find solutions to the system. So first I need to find two numbers that multiply to negative 3 but add to 2. That would happen at positive 3 and negative 1. So your two factors are x plus 3 and x minus 1. Giving you x is equal to negative 3 and x is equal to 1, but you're not finished yet. That is the solution to the equation, but this is just half of the coordinate. It's just the x coordinate. We need to find the y coordinate as well. So we need to take these solutions for x equals negative 3 and x is equal to 1 and plug them into one of the original equations. I'll use the bottom equation since it's simpler. So using that one, we get y is equal to negative 3 plus 3, so we get y is equal to 0. So one solution is negative 3, 0. In the other solution, I'll get y is equal to 1 plus 3, so y is equal to 4. So 1, 4 is the other solution. And if you wanted to double check, you could plug these into both equations just to make sure they're correct. And since we plugged the negative 3 into the second equation, you would want to plug negative 3 into the first equation as well to see if it's right. Same with x is equal to 1. Now for this last example, the setup is the same. So again, y is equal to x plus 2. So we can rewrite the first equation as x plus 2 is equal to negative x squared minus 5x minus 1. I can move everything to one side of the equation, so I'll add x squared, give me x squared, add 5x plus 6 plus 3. But now I see I cannot factor this. There are no two numbers that multiply to 3 and then add to 6. So I'm going to have to go about solving this in a different way. I'm going to use the complete the square method. So first I'll subtract 3. And it's already in that x squared plus bx mode. And now I just need to find what number I need to add to each side in order to create a perfect square trinomial on my left side of the equation. So half of 6 is 3, squared is 9, so add 9 to each side. And that perfect square trinomial, which we just talked about earlier, factors into x plus 3 squared, which is going to be equal to 6. I'll take the square root of both sides, giving me the absolute value of x plus 3 is equal to the square root of 6, which doesn't simplify any further, which gives me x plus 3 is equal to plus or minus 6, which gives me two solutions. X is equal to negative 3 plus the square root of 6, and x is equal to negative 3 minus the square root of 6. Now, I want to find the y value solutions as well, so I'm going to use that bottom equation. So I get y is equal to negative 3 minus the square root of 6 plus 2. So y is equal to negative 1 minus the square root of 6. So one solution would be negative 3 minus the square root of 6, comma, there shouldn't be a comma there yet, comma, negative 1 minus the square root of 6. So even though there's two terms to those numbers, those are just one number and one number. So that's one solution. The other solution, plugging it into the second equation, is y is equal to negative 3 plus the square root of 6 plus 2. Give me y is equal to negative 1 plus the square root of 6. So the other solution would be negative 3 plus the square root of 6, comma, negative 1 plus the square root of 6. So these are irrational solutions. So where they would cross on the grid, it would be at some point not on a vertice, where on a lattice point where the two lines cross. So this is probably the more ideal way to solve this type of system, since we couldn't necessarily see where they would exactly cross. And that is how you solve a linear quadratic system of equations.